I'm Bori. I'm going to present our recent work, Efficient Zero-Knowledge Arguments for Paillier Cryptosystem. This is a joint work with one fellow, my supervisor Man Hao, Rupeng Yang, Haiyang Xue, and Lichun Li. Election happens everywhere around the world, and many different statistics are reported by media or poster companies based on various features of the voters. So let's take a concrete example here. For example, exit polls by age. Suppose there are 4 candidates in a voting campaign, and each voter can only vote for one candidate of his choice. A party P1, which may be CNN, does a telephone interview for the potential voters of their preferences towards different candidates, and it collects this table of data. It wants to figure out the age group that favors each candidate, so it may seek collaboration from another party P2. So here P2, which may be the AT&T company who collects its clients' ages. And both of these parties want to complete this analysis securely without revealing their raw data to each other. So Paillier is a commonly used additive homomorphic encryption and is useful for various privacy-preserving statistical analysis. And here it can be used to secure our two-party data aggregation scenario. So in this example, P1 will first pass all the records belonging to the same entity into one message. For example, for the first entity, it will first convert this table into binary records to denote the preference, where it will use 1 to denote that an entity may support for a candidate, otherwise it will use a 0. Then it will pack all these records corresponding to the same entity into one message, and this message should hold some structures. So firstly, it is divided into several slots. Secondly, in each slot, the binary record is only inserted in the last bit, while others should be 0, so that we can reserve them for future computation in each slot. So after P1 structures or the messages, it will use Paillier to encrypt them and send the ciphertext to P2. Then P2 will first attach the corresponding weights, which denote their ages, on the ciphertext, compute the summation, and send the result back. When receiving the summation, P1 will decrypt and pass it to get the age group that supports for each candidate. But however, a malicious P1 may deviate from the message structure and steal data from P2 after passing the final result. For example, in the second slot of the second message, a malicious P1 may insert the bit 1 in the higher position of this slot. So after passing the result, the corresponding weight W2 will be observed in the higher bit of the final result, which means that data from P2 can be easily stolen by deviating this message structure. So to prevent such a malicious P1, we should require P1 to provide a zero-knowledge proof along with the ciphertext and send them together to P2. So to be more specifically, P1 is required to prove that firstly, each ciphertext is correct Paillier encryption of the message. And secondly, each message should hold correct structures. That is, each message is divided into several slots, and the binary record can only be inserted in the last bit of each slot, which is we are required to prove the relation R star. And there are multiple zero-knowledge proof constructions proposed for Paillier, but none of them focus on proving Paillier messages with structures, and their costs are linear to the number of entities. One may also consider using existing sublinear proof systems, but it is also impractical in our scenario. The reason lies in that it requires to generate a circuit over a prime field to represent statements related to Paillier. But Paillier works under modular a composite number n square, and this will result in infeasible circuit size and cost. So to design a zero-knowledge proof for our considered scenario, considering that one P1 may collaborate with multiple P2s for different kinds of analysis, and the analysis may include thousands or even more messages at a time. So our aim is to construct a zero-knowledge proof that can support batch proof and verification, has sublinear proof size, low verification cost, and can be reusable. So it goes to our solution. Our underlying protocol is BCC plus 16. It constructs an efficient zero-knowledge proof with a series of linear and multiplication constraints as inputs. So to prove relation R star, our aim is transferred into constructing a constraint system to represent R star. Then we can reuse the approach proposed in BCC plus 16 to construct an efficient zero-knowledge proof for our constraints. But what has to be emphasized is that our constraints should work under modular a composite integer n square because we are using Paillier in our scenario. So we'll start by constructing constraints for correct Paillier encryption. The Paillier encryption can be rewritten as this, and the first part is already a linear constraint. Next, we'll focus on representing R to the power of n. Here we use an example to illustrate our approach here. Suppose n equals to 21, and we first write down its binary representation as 10101. Then according to the number of these composition bits, here we square R for 4 times, and we can get R to the power of 2, to the power of 4, to the power of 8, and then to the power of 16. And next, we multiply some of them according to the ones in the decomposition bits. That is, we first multiply R and R to the power of 4, and we get R to the power of 5. Then we multiply R to the power of 5 and R to the power of 16. And finally, we can get R to the power of 21, which is the result that we want here. So if we let alpha to denote the number of binary decomposition bits of n, and beta to denote the Hamming weight of n. So following our steps, we can use alpha plus beta minus 2 multiplication constraints to represent R to the power of n. So to sum them up, we can use this many of linear and multiplication constraints to represent one correct Paillier encryption corresponding to ciphertext C, message M using randomness R. And we denote all these constraints using this notation here. Next, we are going to prove that one message is binary. We'll start by using one multiplication constraint, m times m minus 1 equals to 0. But however, it does not work here. The reason is that our constraints are under modular n square, which is a composite number, and there may exist 2 other non-trivial roots that also satisfy this constraint, and we denote them as x and y here. And we can see that these non-trivial roots are quite large. So to prevent the prover from using the non-trivial roots, we can let the verifier to verify the range of the message. So specifically, we will first let the prover choose a randomness R prime from a relatively small range compared with these non-trivial roots. And this randomness will be used to hide the message later. Then the verifier can choose a random challenge BL. Then the prover is required to compute their linear combination with the message, and the combination result, L prime, will be sent back to the verifier. Then, since the randomness is relatively small compared with the non-trivial roots, so by checking the range of the combination result, if it is not that large, then the verifier can be convinced that the prover didn't use any non-trivial roots in its computation. But here, we still have 1/2 probability to have a cheating prover. So we can repeat this process for kappa times to further reduce the soundness error here. And we can extend this method to prove that polynomially many messages that are all binary. That is, we use the same constraints on each of the message to prove that each message is binary. Then we are going to prove that polynomially messages hold correct structures. That is, again, each message is divided into several slots, and the binary bit is only inserted in the last bit of each slot, and will start by 2 slots in each message. So for each binary record, we use the same constraints to prove that they are all binary. Then for each message, we use one linear constraint to prove that these 2 records are located in the correct position inside the message. Then we reuse the same technique to an extent to prove more slots. For example, there are 64 slots in each message. And here we use the same technique by covering more binary records in the linear constraint of each message. But however, this does not work again. The reason is that our technique for proving the binary bit can only work if these bits are fixed. And our analysis is that only if the message satisfies this length requirement, then given its Paillier ciphertext, its binary representation bits can be fixed. Here, fixed means that given a Paillier ciphertext, there may be possible more than one solution set of the binary representation bits that can satisfy all these constraints that we listed. But right now, the message has more slots. Right now, each message has 64 slots, and each slot consists of 32 bits. So the message does not satisfy this length requirement. Therefore, our technique cannot work here. So to fix this problem, we construct auxiliary messages using binary records to be proved. So that we want to make the auxiliary message to satisfy this length requirement. That is, the auxiliary message length cannot be so long. So here, we use the binary records inserted from 15 messages to construct one auxiliary message. But this specific number can be changed due to different parameter settings or choices. Then we use Paillier encryption to commit all these auxiliary messages. So based on our analysis, right now we can fix all these binary records. After this, we reuse our technique again to prove that all these records are binary and located in correct positions inside each message. So put them all together, we can use these constraints to represent the relation R star. That is, we can use these constraints to prove that correct Paillier encryption with the plaintext holds specific structures inside. And for the performance of our system, we examine our system under two sets of parameters. And for the two-party data aggregation scenario we considered before, with proving 800 Paillier messages at a time, the proof size is less than 2 or 4 megabytes under different parameters. And besides, the verification time required is also very small. And our system achieves sublinear proof size. That is, when proving more messages at a time, the proof size for each binary record will be reduced. And if we prove more messages at a time, the proof size for each binary record can even be less than the encryption cost for each binary record. And compared with using an or proof, our system also gains benefits in both proof size and verification time when proving hundreds or more messages at a time, which suits the aggregation scenario in practice very well. And to use an or proof, more specifically, P1 should first use Paillier to encrypt each binary record, and then he can use a standard or proof to prove that it is 0 or 1. And for the comparison, for example, when proving 800 messages at a time, ours is 19 times or 27 times smaller in the proof size, and also 1.7 or 4 times faster in verification on the different parameters. In conclusion, we derive an efficient zero-knowledge proof for different structures in Paillier system, which supports batch proof verification and achieve sublinear proof size, low verification cost, and can be reused. The core of our work is a constraint system under modular composite number, and our technique is general and can also be extended to derive different relations over Paillier. For example, we can derive an equality proof for sum of records. That is, to prove that there are at least two ones in each voter's preference. And this kind of requirement can be observed in plurality at large elections, which are used in many regions around the world. And one can also derive a range proof for sum of units by using our technique. That is, one can prove that there are more than two ones in the records towards the same unit. And this kind of requirement can be used to prevent the weight leakage from the final combination or collaboration result. And even more properties for Paillier and more relations for Paillier can be proved using our technique. And please find more technical details in our paper. Thanks for your listening.